So, last week, what did we do last week? We did polynomial transformations, inverse, and we did like the zeros and the random equations of polynomials, shifts, inverses, systems, and three variables. Right. Gotta get myself in Saturday morning mode here. So today is a review of, hopefully this will focus. Weird. I wonder why it's not. There we go. Good morning. There's a packet right on that back table with you. There's two packets. The packet on the underside we did last week, okay. And there's a video online for that, so on my webpage. So if you want to go back and, maybe not now, but maybe once school's out and you feel like you still want some review, you could always go back and watch that video. Here somewhere. So today we're doing parabolas and circles, which is going to be a lot of completing the square, a review of that. Exponentials and logs, and exponents and logs is a big chapter. So how many pages do we have here? 1, 2, 3, 4 and a half. Okay. So this question was on there was a question like this on the very first Algebra 2 Regents that came out. It is really technically a geometry question. The geometry kids should be able to do this. So, you know, sometimes they throw some weird stuff in here, but we've learned to say that this is something that we teach as well on top of geometry. But always the first thing we should do is we should get rid of any constant. Okay, so we would subtract 12 from both sides. And if necessary, we would rearrange it so all the y's were next to y's and all the x's were next to x's. I tend to leave a little gap because I'm going to complete the square in here and out there. So I leave a little gap there, but sometimes you'll have to rearrange it completely. The x squared and the y squared will be next to each other, and then the x and the y, and then you just kind of got to get all the x's in one spot, all the y's in another spot, and all the constants over to the other side. And then, do you guys know what I need to add here to complete the square? No? 4. You take half of that, which is 2. And then you square that number. And that's what you add in there, and you also add to this side. So by doing that, what we just did is we created a trinomial that's factorable, okay? Now, if you don't see the quick factoring way, you can kind of do your guess and check, x and x, 2 and 2, plus and plus, and it should always be the same thing multiplied by itself, which means we've made it a perfect square. We've made this trinomial something that can be written as something squared. Now, a lot of people skip that step because we're just so used to it becoming a perfect square, we jump right to there, as you should. For this one, again, it's always take half of the b term. So I'll write that up top. You take half of the b term, you square it, and you add it to both sides. So half of negative 10 is negative 5. Negative 5 squared is 25. You're always going to be adding something to both sides. You're never going to be subtracting anything. And then this is now a perfect square trinomial as well, and it factors into y minus 5 squared. And then on our other side, negative 12 plus 4 is negative 8. Negative 8 plus 25 is 17. So this one's only asking for the center, but I'll go over the whole kind of format. The general format for circles that you should have memorized is this x minus h squared plus y minus k squared equals r squared, where h comma k is not your vertex, right, but your center, and r is obviously your radius. So in this case, our radius is the square root of 17, because that's r squared, so r would be the square root of 17. Our h is negative 2, right? H had to have been negative 2. X minus negative 2 is what turned that into a plus 2. So h itself is a negative 2, and k is exactly a 5. So negative 2, 5 is our center. Okay, but this formula is definitely something to have memorized along with the details of it, which, again, this is the second year you've seen it, so hopefully that's no problem. Okay? The quadratic function, this is the general format, vertex format for a quadratic function as well. You should have that memorized. There's a packet right on the back you can grab. There's a second packet if you want to grab, that's last week's, that you can watch a video for. But this is the vertex form of a parabola that you should also have memorized, because a lot of times you're going to have to complete the square for that too. So in this particular problem, we're given the quadratic in standard form, and they want us to really convert it to vertex form. Just like our circle was given to us in standard form, we had to convert it to kind of that center radius form. So the first thing you need to do, well, and this may vary a little bit, you'll have to tell me how Mrs. Ziggy taught it, but I also, on this kind of problem, always tell my kids to move the constant over. Okay, just like I did with this positive 12 in the circle, I always want to move the constant over. So I always subtract the 23 just to get it out of the way. I will eventually move it back, but to me it's just easier to get it out of the way. You also can never complete the square when there's an a value there other than 1. And right now we have an a value of 3. So we need to factor that out. And that leaves us with x squared minus 4x. And just like I left a little gap with the completing of the square for the circle, I leave a little gap here to come up with that key number again that I'm going to put in here, add in here, in order to make this a perfect square trinomial that's factorable. So if I take half of this term, I get negative 2. Negative 2 squared is positive 4. Now here's the tricky part with this. If I add 4 right here, what do I have to do on the other side?
Add 4.
That's the tricky part. Because by adding 4 in a set of parentheses that has a 3 out in front, I really added 3 times 4. I really added 12 to the right-hand side. Do you follow that? So because there's a coefficient there, you have to be careful of that. It looks like I added 4, but it's in a set of parentheses that's getting multiplied by 3. So I really added 12 to the right, so I actually have to add 12 to the left. And so negative 23 plus 12 is negative 11. And then I have my 3, and again, my trinomial should now be factorable into something times itself, and that's going to be x minus 2 squared. And then I just add my 11 back over. So add 11, okay, and here's your new vertex formula. Y equals 3 times x minus 2 squared plus 11. Now again, I'm going to line that up exactly above the generic format. And like HK was important for our circle, HK is important for our parabola. It's our vertex. So the H is a 2. HK equals your vertex. In this case, it's 2, comma, and our K is 11. So the coordinates of your turning point, 2, 11. Any questions on that? It's kind of nice to see those two side by side from each other, because they're both kind of the same idea, but obviously different formats of circles and parabolas. Number 3 is, hopefully you've seen this a gazillion times this year. I would be 99% confident it's going to be on your Regents. Something with a focus and directrix. This particular problem happens to give you the focus and give you the directrix. So anytime you get a problem like this, sketch it. So I'm going to sketch a focus at 6, 8. And label the point right on there so you don't have to constantly be looking back and forth. Your directrix is y equals 2. Okay, now where is the vertex always in relation to the focus and the directrix? Where's the vertex of the parabola? Always perfectly in the middle. So you can just always count that out if you want to. And really, coming up with the coordinates aren't necessary, but it's a good checking mechanism. So halfway between 2 and 8 would be right at 5. So our vertex is going to be right in here at 6, 5. Okay. Does this parabola open up or open down? Up. Your parabola always kind of shapes a bowl around the focus, and it never, ever, ever crosses the directrix, okay? Remember, and here's the basis for this whole problem. Any point on a parabola, and you've been dealing with parabolas since Algebra 1, but you've never actually known the definition until this year. Every single point on a parabola is an equal distance away from the focus as it is from the directrix. So no matter what point we put on there, and obviously the vertex is the obvious one, it's 3 units away from the focus, it's 3 units away from the directrix. The further away we get, now this might be 5 units away from the focus and 5 units away from the directrix. But that's the key for this entire type of problem. We pick any generic point x, y, and we let that be P. And I have my kids kind of memorize this. We do flashcards where the key term is on the front and they have to know what's on the back of it, just like you would do with times tables flashcards. And on the front of this flashcard it says equation of a parabola given a focus and a directrix. And they have to know that your point to your focus distance equals your point to your directrix distance. And that's going to be the basis. If you want to write distance above each of these, that's going to be the basis for this entire problem. Obviously, you need to know your distance formula. I'm pretty sure that's not on your reference sheet. But your distance from your point to your focus has to be equal to the distance from your point to your directrix. So we have to come up with a coordinate pair always for whatever's on the directrix. And you're never going to know both coordinates on the directrix, but you will always know at least one of them. Since this is a line y equals 2, then the point has a y coordinate of 2, and the x coordinate we're just going to call x. So that now we can do the distance formula between point and focus. So we have the square root of x minus 6 squared plus y minus 8 squared. And then point to directrix is going to be x minus x squared plus y minus 2 squared. Now, in all of these problems, you're going to have a square root on both sides, so that square root can just kind of cancel off and we can ignore it. What's also always going to happen is that one of your terms, one of your set of parentheses will be 0. It's either going to be x minus x or it's going to be y minus y, and right now that's this one, so that can cancel out. And so what we're left with is 3 sets of parentheses always, 2 of which will be the same variable. We've got an x set of parentheses, a y set of parentheses, and a y set of parentheses. Whatever there's 2 of, that's what we square out. We're going to leave the single one alone. So I'm not touching the x minus 6 squared, I'm leaving that alone. But I am squaring out y minus 8, and hopefully you are pretty good at that shortcut by now. You shouldn't have to do y minus 8 next to y minus 8 to see this, but if you do, by all means, please do it so you get it accurately done. And then y minus 2 squared is just y squared minus 4y plus 4. Kind of doing the opposite of completing the square. You're like actually multiplying it out. Now what should always happen is you'll have a y squared on both sides, or it might be an x squared on both sides. And now we're just trying to solve for y. So we want to get all of our y's together on one side. I'll move this negative 16y over to the right. And you want to get your non-y's away from the y's. So I'm going to subtract this 4 over. And so what I end up with is x minus 6 squared plus 60 equals 12y. And we're just one step away of getting 12 all by itself. Everything has to be divided by 12. So we're going to divide by 12 there for obvious reasons. We have to divide this one by 12, and we have to divide this one by 12. When you divide your binomial by 12, the binomial that's squared, you're not actually going to put everything over 12 here. They typically will just leave this as 1/12 times x minus 6 squared. But the 60 divided by 12, they should divide out, and it equals y. So let me ask you, what is my hk here? What's in my h spot? 6, and what's in my k spot? 5. That's the kind of checking mechanism. Now, we didn't have to come up with the vertex up here as 6, 5, but if you should be able to pretty easily, so it kind of gives you a good check to be like, all right, I've got this right. Also, because this opened up, you should expect your a value to be positive. And sure enough, we have a positive a value. It's small, but it's positive. Okay? Positive a values open up, negative a values open down. Okay? Now, just to kind of add on to this, what we have seen over the few tests, and we did all 3 parts already, right? A, B, C. What we have seen over a few tests that they've given is they don't always give the focus and the directrix. Sometimes they'll give you the directrix with a vertex, or sometimes they'll give you the focus with the vertex. And if they do that, let's just pretend, just a couple examples to add on here. If they give us a focus of 3, 8 and a vertex at 3, 10, you need to be able to come up with your own directrix. Okay, so if I sketch this, 3, 8 is going to be here, and that's my focus. The vertex is going to be 3, 10. Where's my directrix? Okay, it's nice and easy if they give you the focus and directrix and you just have to go halfway in between for the vertex. But now they're giving you the halfway in between point already and the focus. So how many units away is that focus? 2. So we have to go 2 units the other way to get our directrix, which would be at y equals 12. Okay? So they can give you the vertex and the focus, and you have to go the other way, that same number of units, to get to the directrix. Or vice versa. They could give us the, let's say they give us the vertex is negative 3, 6, and the directrix is y equals 1. So again, they're not giving you focus directrix, so you're not going halfway in between them. They're giving you the halfway point already by giving you the negative 3, 6. So if they give you that vertex of negative 3, 6 and a directrix at y equals 1, where's your focus?
Negative 3, 11.
Very good. So this is 5 units below, so our focus has to be 5 units back the other way. And negative 3, 11 would be it. And you obviously need, I mean, at the end of the day, these are the 2 things you really want. You always want the directrix and the focus, but they may not give them to you straightforwardly. Okay? We've seen that before. Any questions on focus directrix stuff? Good? Okay. The last one here is just some exponent rules, trying to follow exponent rules. To be honest with you, this is a pretty easy question because your exponents typically are fractions. That's really the Algebra 2 piece, is that they'll make those exponents fractions, or they may start the problem with a radical, like the cubed root, so that you have to raise it to the 1/3 power. So maybe we'll see some of those later on in here. But for the moment, we have all whole numbers, so what's the exponent rule here? When you raise a power to a power, what do? Multiply, so initially it's x to the negative 6 power. In the denominator, when you're multiplying common bases, what's the rule? What do you do with the exponents? Add them, x to the 7th. And then when you're dividing common bases, what do you do with them? Subtract. Negative 6 minus 7 is negative 13. And then when you have a negative exponent, you can't leave that in the final answer. You kind of have to move it to the denominator in this case. So it'll be 1 over x to the 13th, so the value of k is 13. Okie doke? Here we go. So now we get into those fractional exponents, which are a little bit more typical. I give this to my kids as kind of the flashcard that they use. The denominator is whatever root you're taking, and it's x to the numerator out there. So in this case, the numerator is going to stay on the a, so it'll be a to the 5th. And then since it's over 2, the denominator goes out in front, so it's the square root of a to the 5th. Does that make sense? Any questions on that? Straightforward. So just a quick review of that. Oh, it's this one. With square root, we don't actually write the 2 usually, but this is the more typical type I was just talking about. Okay? Now, again, this is the square root, and typically with square roots, we don't write the 2, but I'm going to write the 2 in there. So if this is the square root of x to the 5th power, this is the numerator, that 2 is the denominator. So that's the same thing as x to the 5/2 divided by. This one here is the same, this one here is the same as x to the 7/4. Again, what's outside the radical is your denominator, and now it's just a basic common bases being divided. We subtract the exponents. I say basic, but it's a little annoying because it's fractions, right? If you don't know how to get a common denominator to subtract your fractions, just type it into your calculator. But we should be able to easily make this a 10/4. And then 10/4 minus 7/4 is x to the 3/4. And if you look at your answers are all back in radical form. So again, the denominator is your root. So because the denominator is 4, we're looking for the 4th root of x cubed, which is option 1. 7 kind of stacks some of these radicals on top of each other. Work from the inside out. So the first thing we would do is switch this cubed root of 2. So it's the square root raised to the 4th power of the cubed root of 2 is 2 to the 1/3 power. Yes? Okay? Then when you're taking the square root of that, we're going to take 2 to the 1/3 power, and the square root is the same as raising it to the 1/2 power, and then that whole thing is raised to the 4th. So you kind of work at rewriting this from the inside out, and then power to power to power, they all get multiplied. So 1/3 times 1/2 times 4/1. We're multiplying fractions, no need for a common denominator. The numerator is 1 times 1 times 4 is 4. Over 3 times 2 times 1 is 6. So that ends up being 2 to the 2/3 power because 4/6 reduces. And then the denominator is 3, so it's the cubed root of 2 squared. And 2 squared obviously is the same thing as 4, so it's the cubed root of 4. Okay? In number 8, what type of equation is this? Exponential. Your variables are in the exponents. Now, typically with these, you're going to log both sides, right? Or natural log both sides, whatever you guys do. I know Mrs. Ziggy teaches it just a little bit differently than I do. In Algebra 2, most of the times that we solve an exponential equation, it's going to require that. In some rare cases, though, your bases can be written with the same number. So, for example, in this one, we have 1/2 to the 3x plus 2. And on this side, 8 is the same thing as 2 cubed to the 6x minus 4. And the 1/2, and when I say they can be written with the same base, the base I'm talking about is 2. Because 1/2 can be written as 2 to the negative 1st to the 3x plus 2. And then I'll just leave this side alone for a second. But now both sides have a base of 2. And then based on our exponent rules, powers to powers multiply. So when I multiply negative 1 times 3x plus 2, I'm going to get negative 3x minus 2. And then on the right-hand side, my exponent of 3 times my exponent of 6x minus 4 is going to yield 18x minus 12. Oh, is it? You know what? I wrote through it. You're right. It is a 5. Thank you. So 5 times 3 would make that a 15. 5, 15. Good. Okay. So once you have that common base on both sides, we can just cross it off. The exponents have to be equal to each other, and now it just becomes a linear problem. So I'm just going to add my 3x over, add my 12 over, and I get 18x equals 10. Divide both sides by 18. And your answer is 10/18, which reduces to 5/9. That's a rare one, to be honest with you. But I will say this, when Mrs. Ziggy teaches this, what do you do to both sides to get rid of the exponent? Do you guys just do a regular log of both sides, a natural log of both sides? Do you do a log with a certain base on both sides?
She taught it all the way, so it's just...
Oh, she did. Kind of what you like. I guess with this one, it's like, I know like a lot of, I don't know if you guys, but a lot of people just take the log base 0.5. The problem with that, though, obviously in a case like this, is if you take the log of 0.5 and it cancels that, that's all well and good, but this one, you're taking the log base 0.5 of 8, and the 5x minus 4 being brought out in front of that is just gets kind of ugly. Even if you log both sides, when there's exponents on both sides, if I just took the natural log of both sides, okay, my 3x plus 2 would come out in front, the binomials, we keep it in parentheses, times the natural log of 0.5 equals, my 5x minus 4 would come out in front, times the natural log of 8. The sticky part about doing this for this type of problem, and not that it can't be done, and sometimes it has to be done, because we don't have the luxury of bases that can both be written like the two that this one could, is that the natural log of 0.5, being an ugly number, has to be distributed before you can get all your x terms together. And the natural log of 8 has to be distributed, and then once everything's distributed out, then you can get all your x terms together. But it's going to be a gross number. It's going to be like 8.21734.5x, and it's not going to be very pretty. It would be accurate, but I've never really seen it. I mean, it should be an Algebra 2 topic, but every time I feel like every time there's exponents, like multiple exponents with a variable in it, I feel like they write it so that they can have the same base, because this way is just much more efficient. But if you need to, and you have to take a log of both sides, you can do it. You just have to remember when your exponents are those binomials, you have to distribute your log number, whatever that is. All right, half-life. So the half-life of a radioactive material is the amount of time it takes for 50%. We should already know what half-life is. If a particular material has a half-life of 35 years, then what percent will remain radioactive after 100 years? So this I may teach totally different than her. How do you guys do half-life? Can anybody confidently tell me? Does this seem like an easy problem that you have a quick way to do? Crickets. No? So I sort of made up a formula for my kids. I don't know if Mrs. Ziggy uses it or not, but our formula for exponential growth and decay in general, so I don't use anything different for half-life, is this formula here. Your final amount is equal to your initial amount, so I use a lowercase a, or you can use a sub 0 for initial amount. I do 1 plus or minus your rate, plus your rate if you're growing, minus your rate if you're decaying, to the T over P power is what I call it, where T is the amount of time we're waiting to see how much material is still there. The P is the length of time for the rate. So for example, if they tell you that something grows by 3% every 5 years, then I would put 5 years as my P. If they tell me something grows by 3% every 7 months, I would put 7 months as my P. Now, a lot of times they tell you what the rate is per 1 year, so a lot of times you don't really need to put the P of 1, because obviously if the denominator is 1, it's no big deal. But we use this obviously to convert. If they give you the rate every 7 months, and you want to convert it to every 1 month, you've got to go through it this way. That probably does not look familiar to you guys though, does it? But you can't tell me what you guys would do instead?
I don't, the Hills just like put an exponent, I think.
They don't use a fractional exponent?
I have my notes on it, I can just go check.
Okay, well, I just might look at it when we're done. I'm going to go through it this way. So in this particular case, they're not giving us an initial amount or a final amount. So anytime that's the case, I typically just use like an initial amount of 100, okay? Because it'll be easy to answer their question based off of 100. 100 works nicely with percents. So we'll pretend our initial amount is 100. Because anytime it's half-life, you're losing 50%. So it would be 1 minus 0.5. Okay, if you're losing 50%, rate is 0.5. And this is telling us that we are losing 50% every 35 years. So my denominator would be 35 years. And I try to encourage my kids to put the unit there, because the unit of the numerator and the unit of the denominator have to be the same. So there are some instances where they'll tell you the yearly rate, like every 2 years, but yet they'll want you to convert it to a 1 month rate. And you can't have a mixture of years and months. So in a case like that, one of the things would have to be transferred over. So if this numerator was in months, I might have to change 35 years to however many months that is. In this case, they are asking us what percent will remain radioactive after 100 years. So this case is all in years, so that's fine. And then I would just calculate this out. So I started with 100, and then we're going to see how much is left, and then obviously because it's out of 100, it's nice, easy percent. So 100 times 1 minus 0.5 to the 100 divided by 35, and I get 13.8. Okay? So it's 13.8, I don't know, grams. Doesn't really have a unit on it, but if 13.8 are left out of an initial 100, what percentage is 13.8 out of 100? 13.8. So maybe you can see there now why I start with 100. If they don't give you a starting amount, and they're just asking you what percentage remains, starting with 100 should make sense. Okay? Onward. Log rules. Now, we have 3 log rules. I'll review them at the top. If you have common logs, whoops, I just screwed that up. Log of x times y. The log of x times y splits up into the log of x plus the log of y. Okay? The log of x divided by y splits up into the log of x minus the log of y. And the other one that we do most often is if you're taking the log of x to the a power, and this one we use the most because when we solve exponential equations, this is how we get the variable out of the exponent, that a comes out in front, so that equals a times the log of x. Those are your 3 log rules. Sometimes we use them to expand, like the way I wrote them, and I started with the condensed version. I expanded them. Sometimes they're already expanded, and we need to condense them. To be honest with you, most of the time, they're already expanded, and we need to condense them to help us solve an equation. That's the majority of the time. This particular one, it's already condensed. We need to expand them. So kind of working from the outside in. Overall, this is the log of something divided by the log of something. So the division is going to turn into subtraction. So it's going to be the log of x squared minus the log of root y. Now, root y is technically y to what power? 1/2. So you should probably rewrite that because we don't have any rules that involve the square roots. We do have rules that involve exponents, and so then you just bring both of those, or bring your exponents out in front. So I'd get 2 log x minus 1/2 log y. And that's pretty much it. What is classic about the Common Core is that that answer is not there exactly, but one of those is equivalent to this. Which is it? It's option 4. Because 4 log x divided by 2 is going to make 2 log x, and negative log y divided by 2, because that's technically 1 log y, is going to make negative 1/2 log y. So they kind of wrote it as a binomial over 2, so each term divided by 2 would turn into that. So it is option 4. Okay? Looks like we're starting to get into exponential. I would think this would have been a solving one, but yeah, it is. Okay. Which of the following x values solves the equation f of x equals 90? If f of x equals 90, I'm going to plug in a 90 for f of x. So the equation I'm solving is 90 equals 50 times 0.92 to the x power plus 75. And then we have to just isolate our exponential term. So that starts with getting rid of the 75 first. Dividing that 50 over. And I don't know if this is going to be a nice decimal or not. It should be 0.3. And here's where your options vary. What do you guys do to both sides? Like, who has the Mr. or Mrs. Hill? You 4. Okay. What do you guys do? The log or the natural log? Right, it doesn't matter. How about Mrs. Big Eye's kids? Do you guys take the log with a certain base? Oh, you do? Okay. So then we're all on the same page because we would take the log of both sides. So the log or natural log, and the reason you would pick one of those is because you've got a button on your calculator for both of those versus doing the log base thing we don't like. So let's just say we take the natural log of both sides. So we've got the natural log of 0.3 equals, and the whole reason we did that is so we can use that exponent rule and bring that x out in front as a coefficient times the natural log of 0.92, and then we just divide both sides by the natural log of 0.92. As long as you take the log with the same base on both sides, it's fine. If you use the log button on your calculator, what's the base that the calculator is technically doing? 10. And if you take the natural log of both sides, what's the base of the natural log? It's log base. Nope. Yes. The natural log is the same as log base e, which is why if something is e to the 3x power, and you take the natural log of both sides, they just full out cancel. Okay? Because it's a log base e. So at any rate, we just type in natural log of 0.3 divided by natural log of 0.92, and we get 14.4. Obviously, if you did just the log of 0.3 divided by the log of 0.92, you're going to get the exact same answer. Okay, any questions on that? All right, number 12, kind of still exponential, obviously, but this one is specifically compound interest. So this is one formula that I have my kids memorize for basic growth and decay. But then for compound interest, we have a different formula that you have to have memorized. It's capital A again I use, and then you can use A sub 0. Sometimes you'll use P for principal, is more common in financial things. So the principal investment, 1 plus your rate divided into n parts, n being the number of times it's compounded, to the n times t power. Okay, t is obviously time. So in this case, $500 is put into a savings account, so that's your principal, that earns 6%, so our R is 0.06. Compounded monthly, that tells us we use an n of 12. Raised to the 12 times. Which of the following represents the account's worth after 10 years? We plug in a 10, and we just type that into our calculator. There's no solving involved here. This is just a basic calculate problem. Raised to the 12 times 10 power. I got 909.70 to the nearest penny. Anything with finances, if it doesn't say what to round it to and it's money, you have to know to go to the nearest penny. So this would be .698, which would go to 0.70 cents. Yes? All right. Number 13. How many years to the nearest tenth would it take for an investment to double? Again, they're not giving you your initial amount. They're only telling you the relationship between the initial amount and the final amount. So what you can do is use a principal amount of 100 again. Use a starting value of 100. So then, how long, what would be the doubled amount? 200. So we're waiting till our capital A becomes 200 when our principal is 100. If it is earning a continuous, now this is a different formula, right? The continuous interest formula, we call it the PERT formula. Do you guys call it the PERT formula? Okay, good. So your final amount is 200, your initial principal investment is 100. E is not a variable, E is a number, so we just keep it there. And the rate is 3.5%, so I'm going to do 0.035 times T. Now again, exponential equation, we're solving for a variable that's in the exponents. We got to get this base all by itself. So we're going to divide the 100 over first. And here you definitely want to take the natural log, okay, to get rid of an E. And the natural log is nice with E because it's a clean wash. And so we just have the natural log of 2 equals 0.035t and divide both sides by 0.035. So the natural log of 2 divided by 0.035 gives us 19.8. And it says the nearest tenth, so that's option 2. Are we good? Okay. Oh, these questions. I haven't done one of these. I don't know, Margaret, if our class has ever done one of these, because I'm always suspicious that I don't think it's going to be on the region, so I just don't do it. But for some base B, it is known that log base B of 5 is 1.28 and log base B of 2 equals 0.55. There have been 3 regencies. I've never seen anything like this. But when we took our class last year, like 4 Algebra 2 teachers, for them to kind of give us some heads up as to what was going to be on the exam, they did stress this, but I haven't seen it, so I don't know. For the same base, determine the value of log base B of 40. So this is more of those exponent rules. Whatever you're trying to figure out, you want to kind of try to split it up into 5s and 2s as much as you can. So how do we get to 40 using just 5s and 2s? Like, how would you break up 40 into just 5s and 2s? Like the products or the quotients of 5s and 2s? 4 times... I want 5s and 2s, though. Did you say 4 times 10? Or did you say 5 times 8? Okay, well, I'll show you both ways, because you could do it both. Log base B of 4 times 10. Because obviously then 8... The 5 is good, we like that. 8 is the same thing as 2 cubed, right? So if we do it this way, then going back to those expanding properties that we did in the upper right corner, This is the log of something times something. So it splits up into the log base b of 5 plus log base b of 2 to the third, right? Multiplication, when it's in its condensed version, splits up into two separate logs being added together. And that's obviously doable because our 3 can now come out in front. So log base b of 5 plus 3 times log base b of 2. And then you can substitute your values. You know log base b of 5 is 1.28. Plus 3 times, and you know log base b of 2 is 0.55. So you can just type that into your calculator. 1.28 plus 3 times 0.55 is 2.93. Okay? If we went with the 4 times 10 way, that becomes log base b. The 4 is okay because that's the same thing as 2 squared. And the 10 is okay because that's the same thing as 2 times 5. Now, I would probably condense 2 squared times 2 into a 2 to the third power, right? And as soon as you do that, it becomes the exact same as this problem over here. Do we follow? Okay? I mean, if you didn't see that, if you didn't see that 2 squared times another 2 could be condensed, you could split it up into log base b of 2 squared plus log base b of 2 plus log base b of 5. You'll still get the same answer. If you bring this 2 out in front, and you'll do 2 times, your log base 2 number is 0.55, plus another 0.55, plus 1.28. You're going to get the same number. Okay? I'm actually surprised this one says explain. I would think this would have said justify, because your work has to kind of be there so that you can see what that becomes. But if I were to explain how I found my answer, I split up the 40 into factors of 5 and 2. And then once I had it in factors of 5 and 2, I could use my log properties to expand and then substitute in my values that I know. If you had to explain it, I would think that would be justify, though. Oh, we're getting there. 1.5 pages more. Which of the following graphs is shown on the graph? Now, you have your calculator, so you could just type it in, but I'll kind of give you some more on this one as far as what sort of things we should know about here. This is an exponential parent graph shifted up 2 units. You should know that an exponential parent graph, where's b to the x? Here we go. An exponential parent graph, when the base is positive, is exponential growth. So that would look something like that, shifted up 2 units for option 1, and that's not what we're seeing. Okay? So I'm only showing you this because sometimes they creatively find ways to write it with different variables so that you can't just type it into your calculator. And so they would be kind of looking for you to use some of these strategies. So think about your exponential growth parent graph shifted up 2 units, and that's not what we're looking at. So that's out. This one is our exponential growth parent graph still. Even though the base is different, it's still greater than 1, so it's still exponential growth, shifted down 2. So that would be this parent graph shifted down 2, and that's not what we're seeing. Agreed? Okay? So those are out. The log parent graph, log base b of x, the log parent graph looks like this, okay? Where you have an asymptote on your y-axis. And this one would be shifted which direction? Right 2 units. Very good. And that very well could be it, because our y-axis is the asymptote to start, but once you shift it right 2 units, now this would be your new asymptote. So that's in the running, okay? What about this one? Which way would that be shifted? Left 2. So they would shift it to the left 2, which is obviously not that one, so your answer is 3. I'm thinking they could do this by saying, like they could make your bases b, right? They could do y equals b to the x plus k versus y equals b to the x minus k. versus y equals log base b of x minus k, y equals log base b of x plus k. They could make those your four options and tell you b is a positive number and k is a positive number. And then your calculator is not going to be your go-to anymore. You're going to have to rely on that transformation and shift stuff. Does that make sense? Okay, it's rare, not, maybe we shouldn't say rarely, but they do find creative ways to make you avoid using your calculator, so you have to use these basic concepts. I don't know how they come up with them, but they do, and they always surprise us and find a way to make it so you have to really, really know your stuff. 16, we're given a log function. Which of the following values of x is not in the domain? Look at your log parent graph to help you with the domain and to remind you of what the domain is. The x values always have to be what? Positive. You cannot take the log of anything 0 or below. The log, who cares what the base is, of a negative number is undefined. And same with 0. Log base b of 0 is undefined. The only thing you could take a log of is a positive number. So this 2x minus 8 needs to be greater than 0, because that's what we're taking the log of here. So 2x minus 8 has to be greater than 0. You're going to solve that by adding 8 to both sides and dividing by 2. X has to be greater than 4. So look at all your answers. They're all greater than 4, except for 2. So that one's not in your domain. Okay? Any questions on that? These log cooling problems, the mortgage questions that I know you guys have seen a bunch of recently. Well, Mrs. Ziguy's kids recently, because I think you just did that in class yesterday, right? Did you do mortgage questions yesterday?
Yes.
Yeah.
Something.
Yeah, one of her students came and asked me a question on them. They're always going to give you a formula. I really don't think they're going to ever make you memorize the mortgage formula. I don't know, did Mrs. Ziguy make you memorize it? No. Did the Hills make you memorize it? Okay, so they're always going to give us a formula. And the formula might not be the exact version that you're used to seeing. There's different formulas for all these, exponential functions. Just use the formula that they give you and make sure you're reading carefully so that you know exactly what every variable stands for. What does capital T stand for? What does X stand for? What does that say? T sub... Is that an I? Yeah, but what's that subscript on the I? T sub I, T, I don't know. Let me read the question. It's probably initial, I for initial. A liquid with an initial temperature of 194 cools in a room whose temperature is held at 68. So that's a T sub R for room temperature. T sub I for initial temperature. The overall temperature of the liquid, so that's your capital T, as it cools, can be modeled as a function of time, so X is your amount of time. Using this, T sub I is the initial temperature, T sub R is the room temperature, and K is the decay constant. So, given all that information, T of 15 equals 102. So this is really T of X equals 102. So your X coordinate is 15. And your capital T is 102. So this is 102 equals your T sub I, they told us was initial temperature 194. It's a big maze in my opinion. Room temperature 68. E is not a variable, it's a number, so that stays. Your K is what we're looking for. We have an X value of 15. So this is telling us that after 15, is it hours or minutes, or it doesn't say, does it? So maybe 15 minutes. So 15 minutes, we'll say, is your time, plus your room temperature again was 68. So we're solving for a variable that's in the exponent. So before starting to solve, I'm just going to clean this up a bit. 194 minus 68 is 126 e to the 15k plus 68. So that's cleaned up. Now I'll start solving. Again, you always isolate your base to the exponent. So that's going to start with subtracting the 68, which gives us 34. And then we always have to divide away a coefficient if it's there, so I'm dividing away 126. Now this gives me a crazy decimal. So I can jot down 0.27 if I want to, but I'm definitely not going to clear that decimal. I want to use that exactly. So I will write down a 0.27, but I am not going to ever type into my calculator 0.27. I would go back and use this number instead. So from here, trying to get rid of an e, we take the natural log of both sides, so that cancels. And then I'll divide both sides by 15. So k is going to equal, I'm going to take the natural log of this number, not the 0.27 that I wrote down. The natural log, I can go back up and select it. Natural log of that number and divide it by 15, and I get negative 0.08. Rounded to the nearest hundredth, so it's actually negative 0.09 if I round that properly to the nearest hundredth. So if they tell you to round mid-problem, then do it. But that does not mean that we rounded this that early. The only reason I rounded it was to write it down more efficiently. If I had done the natural log of 0.27 and divided that by 15, sometimes I'll get lucky and I'd get the same k value. And here I do. Luckily, to the nearest hundredth, they both worked out to be negative 0.09. But if I were to go to the nearest thousandth, it would have been different, right? This one would have been 0.087. This one would have been, oh no, thousandths would have been the same too. The nearest 10,000th would have been different. But sometimes it's drastically different. And so you cannot round mid-problem. You only round at the very end. And so that's what we did there with the k equals negative 0.09. So now we're going to use that k. So you always then use that k to answer the question. What is the temperature? So if I go back up to our problem, we're looking for capital T of x after 25 minutes. So T of 25 equals. Again, your initial temperature was 194 minus room temperature of 68. E to the, it's now negative 0.09 that we're using for our k, times the x of 25 minutes that we're looking for, plus the room temperature again of 68. And now this one is not a solving exponential problem. I just crunch numbers into my calculator. So typing that in exactly as is, and keeping your parentheses and everything all in the same spot if you want to not do any order of operations on your own. E to the, where's my E button? There we go. Negative 0.09 times 25, get out of the exponent, plus 68. So all in one shot, I put it in there, making sure I have my parentheses all appropriately there, and I get 81 to the nearest degree, so 81. Good? Very common on that kind of question to be asked to find that k first. Okie doke. And here we are with a mortgage payment. So in a mortgage, the monthly payment M is calculated using the formula here. M is the monthly payment, P is the principal, N is the number of payments, R is the monthly mortgage rate, This is actually a typo. And if we have a minute at the end, I'll show if any of Mrs. Zigai's kids have her equation here. This is this R. Take the over 12 out of your equation, because if they're defining R as the monthly mortgage rate and they give you a yearly rate of 5%, you have to know on your own to get that yearly rate into a monthly rate. We just have to divide it into 12 parts, right? It's kind of that compounding idea again. That 5% that you're going to accrue over a year's span is split up on a monthly basis. So, since she said, and I said she because Mrs. Zigai kind of put this worksheet together, R is the monthly mortgage rate, so we're not gonna plug in .05 for R. We have to plug in .05 divided into 12 parts. So she kind of put that divided into 12 there for you, but since R is our monthly mortgage rate, we're gonna take 5%, .05, and divide it into 12 parts, so that our monthly mortgage rate is this R value, which is a gross decimal, so I'm just going to keep it as .05 over 12. And then I will plug in the over 12 part. Do you follow?
Multiply it to 5% by 12.
No, because then that's going to be 60%. Your monthly rate is not 60%, right? Your yearly rate is 5%. So you split that 5% up into 12 parts. You divide it by 12. Why would you multiply it by 12?
I don't know, I just remember doing this, and I should make it that.
It depends on how they phrased it. If they gave you the monthly rate, and then the equation used the yearly rate, and you had to go that direction with it, then you would do that. So if they give you the monthly rate of, I don't know, 0.5%, and then the equation requires the yearly rate, then you would want to multiply that 0.5 by 12 to go that direction. So it depends on how the problem reads. But this is telling us that R is the monthly mortgage rate, yet they're giving us the yearly. So to go back from a yearly of 5%, if you're going to accrue 5% over a year's time, split that up into the 12 individual parts to get your monthly rate. Does that make sense? Kind of depends on how it reads. I'm not going to say that you didn't get a problem like that, because you might have. You have to read that carefully. And again, if anyone from Mrs. Zigai's class has their homework from last night, I can show you a problem just like this. And it might be the same problem. I'm not even sure. So at any rate, we're going to now plug in all of our information. They're asking for the monthly payment, so we still want to know what M equals. Our principal loan amount is $250,000. Our R value is .05 divided by 12, because that's what I computed. And then our our R again is .05 divided by 12 to the nth power. Now, how many monthly payments do we have? How many payments do we have? N is the number of payments. 360. Tell everybody how you got that. Right, 30 years times 12 months in each of those years, 12 payments per each of those 30 years. So 12 times 30, that's 12 months, times 30 years, gave her the 360. So that's to the 360th power, divided by 1 plus .05 over 12, to the 360th power, minus 1. Good? Now, this if you ever want to type something like this into your calculator in one shot, put a larger set of brackets or parentheses around your numerator and a larger set around your denominator. Then you can plug it in exactly as is. So for me, that would be 250,000. Make sure you get the right number of zeros. Another set of parentheses, .05 divided into 12 parts. Another set of parentheses, 1 plus .05 divided by 12, raised to the 360th power, and close the entire numerator, divided by. Some of you guys probably do your fraction thing, don't you? Mm-hmm. Yeah, I don't know why. I don't think that existed when I was in school, so it's not my habit to do that. In the denominator, large set of parentheses around the denominator, 1 plus .05 divided by 12, raised to the 360th power, minus 1, close the denominator. So you don't need that big set of brackets if you're going to go to your second fraction or however you get there. And I get $13.42 and 5 cents. Again, it's finance, so I'm going to go to the nearest penny. Good? Any questions on that? Okay. If the principal was still $250,000, but the yearly rate was 6%, determine algebraically the number of years it would take. So, to pay off the loan with a monthly payment of $2,000. So they're giving you the $2,000 monthly payment this time. So our M is $2,000. Our principal is still $250,000. The yearly rate is 6%. So if the yearly rate is 6%, the monthly rate, R, is 0.06 divided into 12 parts, right? So that would be 0.06 over 12. And then 1 plus 0.06 over 12 to the nth power divided by 1 plus 0.06 over 12 again for our R to the nth power again minus 1. Now these are the doozies because we do have a variable and an exponent and we got it not only once but twice, okay? So the first thing I would do with this type of problem is clean up what you can so there's less moving parts, less multiplications. So I would first multiply this out. So this is like this times this times this. I can't multiply these two by this one. Why not? What's that? Right, because this one has an exponent, and I have to do exponents before I can do multiplication. So I can't multiply this by anything, but the coefficient here, 250, ooh, I have 25,000, 250,000 times 0.06 divided by 12 gives me 1250 here. I should also change my 1 plus 0.06 divided by 12 into whatever it is, 1.005, so I get like a decent decimal base for that one, which is going to be the same decimal base for this one. Whoops, equals 2,000. So here's the key with this one. This would not be solvable if our bases weren't the same. Okay, they should both be the same number, 1.005. So how did you guys do this? Cross multiply, me too, that's what I taught my kids. When I cross multiply the 2,000, at the moment I'm just going to keep, this is a binomial, so I'm going to keep that 2,000 out in front of the binomial. I'll distribute it in a minute. Equals, and then this side is just the same, 1250 times 1.005 to the nth power because I just multiplied it by 1. Now, you want to get all your 1.005 to the nth power together, right? Just like any variable problem. You want to get everything together. I can't get them together yet until I distribute this 2,000 through. So I have two, and again, I can't multiply 2,000 by 1.005 and get a new number. I have to be comfortable leaving it as 2,000 times 1.005 to the nth power, and then minus 2,000 when I distribute to the negative 1. Equals 1250 times 1.005 to the nth power. And now I can get them all together, right? I can subtract this term over to get them all on the same side. So if I subtract 2,000 of these, I'm pretty much combining like terms here. It's a complicated version of combining like terms, but 1250 of these things minus 2,000 of these things makes negative 750 of these things, the 1.005 to the nth power. And once you're here, isolating and solving your exponential equation is pretty straightforward. So the reason I said early on, this wouldn't be able to work if our bases were different, is because down here we wouldn't be able to quote-unquote combine like terms if those bases were different. So you should always have that same base. Divide both sides by 750. 2,000 divided by 750 is 2 2/3. I'll just do 2.6 repeating. And then you guys natural log both sides, right?
Yeah.
ln, ln. And then that n comes out in front. And it'll end up being the natural log of 2.6 repeating divided by the natural log of 1.005, all equals n. So the natural log, again, I'm going to steal that exact value, divided by the natural log of 1.005, gives me an N of 196. Now, anytime 6.655856. You gotta go back and read the question, because N stands for our number of payments. The question is, how many years? The number of years rounded to the nearest tenth. This is the number of months, because that's my number of monthly payments. So if I want to change that into years, I'm going to put months after it, I'm going to divide it by 12 months to turn it into years. So taking that exact decimal, not rounding yet, dividing it into 12 parts, and it's 16.38. I actually think, Mrs. Zigai's kids, this was the exact problem from your homework from last night. Maybe. That's 16.3879 years, okay? Round to the nearest tenth of a year. So the nearest tenth of the year would be 16.4 years. Good? Any questions on that? 16.4 years. So I actually think this was the exact same question as Mrs. Zigai's kids' question or homework from last night, but the homework you guys had from last night used the R appropriately in the initial problem. It said R was the monthly rate. You had to take your yearly rate and divide it into 12 parts on your own, of course. I think when she wrote this, she was probably trying to help you out by putting it over the 12 on its own. But just pay attention to that detail, what's yearly, what's monthly. If the equation calls for the yearly and they give you the yearly, great, plug it in. But if the equation calls for the monthly and they give you the yearly, then you have to know on your own to divide that yearly into 12 parts. So, a silly detail that can throw off your whole problem. How was that? Done and done? All right, good. We're done with 3 minutes to spare. Again, if you had friends that couldn't make it, tell them that this was recorded and that I'll put it on my webpage is where it will be.